My name is John Noe, N-O-E, and I'm from Stony Brook University on Long Island. I'm up here this week for the optics meeting that was taking place this week. And I brought some demonstrations that I do in my lab, which is called the Laser Teaching Center. It's a lab where basically a range of students anywhere from young high school up through graduate students create projects. Some of them are submitted to national competitions and whatnot. And through these projects they get hands-on experience and do self-directed learning. But I also work with groups, and for that purpose I've developed a number of little demonstrations to get people's attention. So some of the different demonstrations, well, let's start with this one. So just an ordinary magnifying glass. And I have here a light bulb, and I'll take a student and I say, okay, I'll hand them the magnifying glass and I'll say, make an image, make me an image. Okay, and what they're going to do is they're going to try and put the magnifying glass somewhere, and eventually, if they haven't done this before, it may take a while, eventually they're going to get to a point, I don't know if you can see this on the video, but you're going to get to a point where you can see the light bulb. So a tiny little spot of light. Now if I do the other image, there are actually two images. So I'll then point out to them that there's a second image. Find me the other image. So they could be, oh, another image? I worked so hard to find this image. What do you mean there's another image? Well, they might need a hint that the other image comes from reversing these distances. So if I put the lens that far from the light source, now I get a different image, okay, which is very magnified. So if you look closely, there's the light bulb. Okay, and that bright spot there, that's the hot glowing filament. And let me get on the other side so I can do it a little better. Gotta hold it just right. There we go. You see the light bulb upside down? You can actually see the whole fixture there, okay? Now the point of that exercise is that kids in high school know the quadratic equation. Okay, that's solving an equation ax squared plus bx plus c equals 0. That has squares in it, square of x in it. And I can take a familiar formula about lenses and focusing, and by rewriting it in a different way, you can see directly from that formula that there are two solutions, and those two solutions are the two places where you put the lens. So by rearranging things a little bit, you can make a direct connection between what you can observe and what you can derive. Okay? So that's one example of things. There are many, many others here. So they're floating, okay? So it looks as though there's just floating in space. And what this really is, it's an image of the actual pigs which are inside, sitting in between two mirrors. Okay, and the mirrors project, if you will, a real image out here. Okay, and you can really challenge people. You can say to them, oh, they really love this thing. You can say to them, well, if you looked at it through a magnifying glass, would the pigs look bigger? And most people are pretty dubious about that. They say, oh, I don't think so. So what you do is you actually do the experiment. Okay, I don't know if I've got it lined up right, but by God, those pigs do look bigger. You can hold a small mirror behind, okay? And you'll ask people, well, what do you think? You think you'll be able to see the back of the pig if I hold a mirror here? And they say, no way. Okay, and then you do the experiment, and sure enough, you can. Okay, you can even shine a laser beam on the pig, okay, and the pig will light up as though the pig was right there. Okay, so all these kind of paradoxical things, challenging people to think about something and then showing them the reality of it. It's just a lot of fun to do. This is another thing. This is called a retroreflector. Okay, it's basically three mutually perpendicular reflecting surfaces, and the camera is going to see the camera lens no matter which way I turn this thing. Okay, it's only seeing the camera lens. Okay, and if you do it this way, if you look into it, you'll only see your eye. You cannot see anything else. There's actually a set of these about this big on the moon that was brought up there in 1969. And the reason for that is that you can send light through a telescope, a laser beam, okay, and it will retroreflect from these reflectors and go directly backwards, back through the same telescope, and can be registered as a signal. And by very precisely measuring the time between when the light went out and when it came back, of course, you can measure the distance to the moon. You can measure it to an uncertainty of a centimeter, that much, at any moment. And that makes possible all kinds of precision tests of relativity and
bringing the quadratic equation to life. Tell me how you bring the quadratic equation to life. Because there's nothing more boring than the quadratic equation, right?
I think this will make a difference. So you ask people to focus light. So come over here. Do you have a free hand? Put your bag on. Okay. Take the lens and make an image. Make an image of the light on the wall. Okay. Okay, there you go. Beautiful. Okay. So that's an enlarged image. Now there's actually a second image. Can you find the other one? Where's the second image? Okay, symmetry is a clue. So if you interchange the object and image distances, or if you imagine the rays, instead of going this way, the rays are going this way, okay, so that's a clue. Where would the other image be? Now you've got to interchange, so you've got to put the lens this far from the screen instead of from the lamp.
I'm sorry.
So if the lens is now this far from the lamp, it also works if you put the lens this far from the screen.
Oh, okay, I'm sorry.
There you go. There's the other image.
Okay.
Now that one is demagnified. It's smaller.
Right.
Okay. Okay. Now if I bring the light closer.
Laser lab sort of thing where you need to wave your tag.
Okay. Now this image is not as small,
name tag that
and the lens moves back a little bit.
like
Yeah.
Now go find the corresponding one.
maybe like an ID
So there it
thing
is. Okay. So now it's a little further from the light. If I bring this even closer, okay. At some point, you're going to find there's only one place you can get an image. The lens has to be smack in between.
Right.
Okay, symmetry.
Right.
Okay, and if I bring it even closer, there's no image.
Yeah.
Okay.
Because you're inside the.
All right. Now, what has this got to do with the quadratic equation? So, if I take the thin lens equation.
I actually know that's mine.
If I take the thin lens equation, 1 over, I don't know how you like to write it, but 1 over SI plus 1 over SO equals 1 over F. Okay, everybody's familiar with that. But it doesn't tell you as much. We can make it better, okay? What we want to do is we want to write S equals SI plus SO. So S is the total distance, ST. Okay. And I'm going to eliminate SO. So I have 1 over SI plus 1 over ST minus SI equals 1 over F. Now it's a straightforward thing to cross multiply. Write down SI as a function of S total and F. Okay? And what you're going to get is something that has a square of SI in it. Okay? And kids are stumped about this at first, but you can match it up against AX squared plus BX plus C equals 0, show that it's the same form.
I'm sure this is nothing new.
And the result then is the solution for SI involves something plus or minus a square root of something over 2 times something, you know, the usual solution. That's the quadratic formula, right? Okay, and so the plus or minus gives you the two, two positions, okay? Okay, and if the thing under the square root becomes 0, the thing under the square root is S minus 4F. Okay, if that becomes 0, if S is small enough, is equal to 4F, okay, then you only have one image. And if S is less than 4F, then you got the square root of a negative number, you got no image. Okay, so the quadratic equation really reverberates with the physics that you can do with your hands. Okay, so that was just a simple thing, but it was really cool when I came across it.